Hi, hello everyone. Welcome to the review session for Circuits 1, and thanks for joining. Also, if you want a recording of this whole session, please make sure to scan the QR code that was probably shared to you from your instructor and put in your name there so that I can send out the recording link to you after the review session has ended. I'll also include the link to another sheet that you can fill out right now, uh, so that I can send out the recording afterwards. And uh, while I'm going through the problems, if you have any questions, feel free to come off mute and ask me uh, whatever question you have. Can you hear me right now? Okay, so someone says that he can hear me. Okay, awesome. I'm just gonna All right, I've sent out the link to the sheet in the comments. If you want a recording, please make sure to put in your name and your ASC email there so that I can send it out to you afterwards. And all right, we can start off right now. Hey, Xavier, do you have any question? Yes, no one has a question. All right, so I know all of you guys have this exam next week, and depending on the professor, the content might be uh, after your first midterm or the whole course itself. So I'll basically be focusing on more stuff that was covered in the recent last few weeks, so that um, you have a better idea of it, and I believe you're going to be tested on those more. So I'll briefly go over some of the key concepts that you would need for the final exam, and then I'll be solving over some of the problems. So, uh, most importantly, RLC circuits. So, you see a table here, and I, I would say that this is the most important, like one of the most important tables that you would need. I mean, if you can remember it, great. Otherwise, if you're allowed a cheat sheet, I highly suggest to include something of a similar kind within your cheat sheet so that you can recall the formulas. So basically, it goes over the the voltage and current relation of resistor, inductor, and capacitor, and what happens in the DC steady state, and phasor relation, impedance, and phase. Also, I think somebody wrote down the email in the comments. If you can please go into the Google Doc link that I shared and put it down there, that would be great. Because otherwise, it's not going to be possible for me. Yep. All right, awesome. All right, we'll carry on. And if you want to take a screenshot of the table right now or a picture, feel free to do so right now so that uh, you have a reference on how to make the cheat sheet. So this is actually a part from my actual cheat sheet that I had. I've just like separated it out according to the sections. And if we move on, you have a brief uh, representation of uh, the phasor, polar, and rectangular forms. And then we have the phasor, how it's represented, how you can, what does the magnitude, period, and frequency, like how does it plug into the formula for resistors. This is usually the phasor equations. Uh, so usually there's no phase difference for resistors. For inductors, always remember that voltage leads the current by 90 degrees for inductors. And also remember the fact that current can never instantaneously change in inductors. So inductors is like more, you can say that it's more like a circuit component that uh, stores current. Like it's not technically right to say that, but it's easier for us to think that way. That suppose you're storing current, right, and you change the current, it's not going to change instantaneously. You gotta give it some time to like adjust to the change and then react to it accordingly. Same thing happens for capacitor, but for voltage. So also current leads the voltage by 90 degrees for capacitor. And why is that? Because capacitor is basically can be said as a voltage storing circuit component. So it will always store voltage. And whenever there's a change in voltage applied to it, it's not, the output is not going to be instantaneous. It's going to take up some time and then the output would be reflected accordingly. All right. So some of the other formulas that I want to focus on is about the AC analysis. So basically, same stuff from before. Does that remember that I've seen a lot of the time many questions being asked about the instantaneous power, average power. So be sure to have these formulas written down somewhere or take a screenshot so that you can write it down on your formula sheet afterwards. So it is pretty common question to have in the exam where it asks you to solve a circuit and then following that they will ask you to find either the average power or the instantaneous power, and having the formula with you really helps out a lot. All right, moving on. One thing I've seen, like including myself, I used to struggle a lot when I was actually doing this first and second order transient circuits. It's something actually like not the easiest thing to solve. So uh, the thing that helped me out really is that uh, from your notes or wherever you want, like I did it from my notes. I noted down all the steps that I need to follow using and while solving these problems, because it's really important to know how how what do you want to do after each step, because it's usually a long process, and as we're not super used to solving these kind of problems, we kind of mess up the steps. So I would suggest having a proper strategy written down, either from your notes or however you want to solve it. Like if you're really good at it, maybe just note down some points or some pointers that how do you want to go through each step, right? So if you want to take a screenshot of this, also go ahead or take a picture, whatever you need. So uh this is gonna be the first order transient, and I believe this is what they probably would be asking you in the finals. And if you have any questions, feel free to go off mute and ask it. All right, moving on, we have second order transient, which has proven to be more challenging to solve. So second order transient, you have three types of systems: overdamped, critically damped, and underdamped. And for this, I can assure you that you would need the formulas to solve any sort of problems relating to the second order transient. And if your professor doesn't allow a cheat sheet, uh, I I assume that they would probably not have any questions from the second order transient, or even if they have, they probably should be giving you the formulas. Um, but then again, I can't assure you, like, if you're not sure about the fact that if you're allowed to take cheat sheet, or if the professor is going to give a formula sheet, please make sure to ask your professor about it so that you know how to plan it around. Okay, so again, if you want to take a screenshot, feel free to do so. I wrote down a couple of strategies, just some steps from the lecture that you can follow to solve the problems. Okay, so now comes the most important part for circuits. I believe whatever you study wouldn't help you much unless you know how to solve the problems. So practicing problems is an integral part for circuits, and unless you're really uh, like you have really solved a couple of problems and you know how to go over the stuff, it's turns out to be super difficult during the exam to solve problems you might have never seen maybe. So at first I'll go through some uh, some multiple choice questions that I had uh, that I was given access to while I was taking the course. There was a sample paper that was from Professor McDonald from spring 2023. And I'll just go over the answers and explain you why that would be the answer. If you have any questions, either leave a comment or come off mute and ask her. All right. So the first question asks the current through uh, slash gap and the voltage across a gap cannot change instantaneously. So exactly what I mentioned before going over my cheat sheet notes. So uh, for a cap for inductor, current can never change instantaneously, if you remember from the previous section that we discussed. And uh, voltage across a capacitor can never change instantaneously. So this is important to know uh, uh, why the answer is that. So I'm just like it's for the multiple choice questions. I believe it's really important to have a good understanding and then have a good fundamentals. So moving on to the next question, it's ask what the slope of a simple zero is. And if you've gone through the Bodhi plots, there's not much you would have to understand in this case. It's just what a simple zero is and what a simple pole is, what a quad pole or a quad zero is. Uh, if it sounds not super familiar to you right now, I would ask you to like go over the notes because uh, uh, it's highly likely that you're gonna have a question from Bodhi plots. So basically, for this one, for a Bodhi plot, simple zero is positive 20 decibels per decade. That's the slope. And if it was a pole, it would have been negative 20. Now the simple question, what is the complex number represented by j square times j? So uh, j square can be represented, j is just a complex number which can be represented as square root of negative 1. So if we do negative 1 squared times j, for example, right? So this will get rid of the square root gets cancelled because of the square power square there. So it's negative j. So that would be the answer. Next question asks, which quadrant does the phasor 3 negative j5 reside? So if you recall how it is drawn on a y and x axis, is that the first one is the x. So it says positive 3, so it will be somewhere around here. And then the y-axis would be this, and it says negative j5, which means like -5. So -5 would be around here. So it's going to be a point in around here, and the quadrants are uh, numbered as 1, 2, 3, 4. So it's going to be fourth quadrant. Okay, so yeah, so the last question, last multiple choice question. What happens to the impedance of an inductor, capacitor, and resistor respectively as frequency decreases? Frequency decreases, right? So frequency decreases means, uh, and frequency can also be written as, uh, so 2 pi f is omega. This is the angular frequency, and that's the one that's used within the formula for the inductance. So if frequency decreases, the omega would decrease as well, right? So what would happen is that uh, for resistor, it doesn't depend on the frequency. Does not depend on frequency. It's a always remember that the frequency only affects the capacitance and inductance, not the resistor. Resistor is just basically it's a DC component, so there wouldn't be any effect on that. And then the Z impedance of a capacitor ZC is basically just 1 over j omega C. So if omega decreases and it's in the denominator, so it means that um, overall ZC increases, if that makes sense. So if the denominator decreases, for example, if it goes to a smaller number than it was before, the the result would increase. So we know that CR no change, ZC increases. So there both options. Now comes the ZL, which is the inductance. So ZL, the inductor impedance is written down as J omega L. And just so that you know, the J is just the complex number, and omega is the one that we found out here, 2 pi f, and L is the inductance value. And it says omega goes down, right? So CL would go down as well. So we have our answer here. Okay, so moving on to the next. I'll go over a couple of problems here, and then I'll do actual like word problems. That would probably help you better. All right, so it says, what is the phasor representation of the following voltage? So um, if this is basically just the phasor representation that they're asking. So it's represented by magnitude and phase. So for this case, we know the magnitude is 10. The phase is positive 80. So 80. Okay. And now then it asks, what is the time domain representation of the following phasor with the frequency of 30 hertz and B is equals to 7. So F is 30 hertz and B, the way it's written is kind of not the best way to represent it. It was actually should have been written like this. So if you remember from the formula that I showed you before, the representation, see like how it comes handy, right? So the representation, how it's done. So it says uh, you can write it down like this, right? So the magnitude sine WT, right? But the thing is, here it's represented as a sine. And how do you know which one to select? It depends on the angle actually. So uh, for this case, it would actually be a cosine for the answer. So it will be time domain representation of the following phasor. That would be the magnitude cosine of 2 pi f, which is 30, and plus the phase, which is 25. And then it asks the rectangular to polar coordinates for this one, which is v is equals to -4, -t6. So remember when we need it for polar coordinates, we just need the magnitude and the phase. So the magnitude would be this squared plus this squared square root. And calculating it using your calculator would give a value around 7.21. Then you need the phase. How do you find the phase? Is that you take the inverse tan of the complex part over the real part, which is 6/4, and the negatives cancel out. So if we solve it out, it gives it a 123.7. So altogether answer would be phase, the polar coordinate would be close to 7.21, which is the magnitude, and the phase of 123.7. All right. Moving on, we have this question about body plots. It's not the most difficult question. It's just intuition at this point. As long as you know how the poles and zeros work, you should be able to answer questions like this. So it says, what are the poles and zeros of the following function? This, right? So it's already in the simplest form. If you go through the body plots lecture, uh, you would know how the equations are written down in the simplest form. So basically, if it's in the numerator, it's gonna be the pole. So the pole would be at uh oh, my bad. Uh Numerator, it's gonna be 0, which is at 10 radians per second. And this is gonna be the pole, which is at 1200 radians per second. And there's basically like a you should have a lecture on the notes on how the body plots equations are written down, and you would be able to find out what the zeros and poles are, even if it's a quad pole or a quad zero. And then comes the another question, says which type of filter is represented by the following body plot. And so there's 3 types of filters: high pass. No, my bad. There's gonna be actually 4 types of filters: high pass, low pass, band pass, and band reject. So what happens in this case? So basically for this one, it only allows, see, like this is the magnitude, this this axis. So when we see that it only allows frequencies, the signals that have frequencies between these values to pass. These are the only frequencies that pass, right? Like those are the only magnitude that shows up that basically suggests that this would be a band pass filter. So uh, uh, if you're curious, like how would it look if it was a low pass? So it would have a curve around here, which suggests that the frequencies around these low frequencies will be passing. If you're asking about like a high pass, the frequencies, the higher section will be passing. And band reject, right? So band reject would have something like, suppose, uh, comes around like this. So it allows all the frequencies at those points and then blocks, rejects the bands between these points. All right. Uh, moving on, I'll be solving a couple more problems that I have from another practice exam. Basically, just going over some of the fundamental stuff, how to solve like nodal and KCL uh, problems. And I'll be going on until 1:15, and I'll keep the rest of the time for any questions that you have, and I'll try to answer uh, best I can. All right, so the first problem is quite simple. Just as a refresher, the questions comes uh, like this. So I'll be solving it as if I'm seeing it for the first time, and I'll be taking it super slow so that it's easier for you to understand what each step of my solving looks like. So we have uh, the resistors. Wait, what are the resistor values? R3, 7, 6. Okay, so the question I have doesn't have the resistor values mentioned this, so I'll do another one with the resistor values. So 1 ohms is R1, 2, IX. Okay, like this. And then uh, we need to find out IX. And suppose this is R and it's mentioned to be this 1 ohms. And now, uh, how do we do it? There's several ways you can find out. So uh, the first would be doing KCL. So for example, if you do the KCL here, we know that 7 amps is coming in, 3 amps is going out, and IX is flowing in, right? So uh, it's really important so that you can do it fast enough to know that uh, what sort of circuit analysis technique that you have to use. So uh, you could have jumped on to just finding it out using uh, uh, using no like using loop analysis, and it would have taken you a lot longer. So in these cases, this thing makes it the easiest, right? So you know that uh, current flowing into a junction is equal to the current flowing out of the junction. Into junction equals to out of junction. So what's flowing in? 7 plus Ix, and flowing out is the 3 amps. So 3 amps. So Ix would basically just be 3 minus 7 amps, which is negative 4 amps. And it's okay to have a negative here, which suggests that Ix will be flowing in in the opposite way that it's being shown. So nothing to be concerned about for that. All right. So I was planning to do a first order differential in case that helps, because these are pretty simple questions that we have here. I believe doing a first order transient might be uh, more helpful for you. So I do have only till 1:15. So going over a whole problem from the scratch would take up a long time. So I have one problem worked out within this review, which I uh, actually had done before for another review. So I'll be going over that instead. So it looks a bit messy, but the question here was uh, you have the circuit here, which has a 12 volts voltage supply, a 6 volts voltage supply here, a 1.25 Henry inductor here, zero point 0.1 farad capacitor here, 6 ohms resistor here, and a 1.5 ohms resistor here. So, and the first step in these problems, that these are transient circuits because uh, it would be switched off. Uh, it's switched on until the time zero, and then it's switched off. It goes up. So after that, it disconnects, right? So if we do the KVL around the loop, uh, what we can do is we see that when the time goes more than zero, this thing goes up. So basically, this whole section of this circuit gets disconnected, right? Because suppose current is flowing from here, it wants to go through here, but it can't because it's open. Same goes from this way, doesn't have any pathway, right? And current always has to have a complete path to flow. All right, so KVL starts from here, 12 volts. Then there's certain voltage drop here, which is VR1, certain voltage drop here, which is VR2, then a certain voltage drop here, which is VC, and a certain voltage drop through this inductor, which is VL, and all equals to zero because we come at the starting point again, right? So if we replace the values, 12 minus, uh, so what I did here is that I combined these two resistance because they're in series. So you can just add it up, 6 plus 1.5, which gives out 7.5 uh, times the current, which is IT, uh, IT, that's flowing through the whole circuit. And then you have the voltage drop through the capacitor, which would be VC uh, times the TO, the T at zero, T0 representation. And then you have uh, this whole thing is going to be the voltage at the capacitor. So this is the initial charge. Remember how we mentioned that capacitor always has an initial charge? Not always, because it was connected before. So it was still the current was still flowing through here, which was actually charging the capacitor. So this is the initial charge. And then if you copy down, if you see from the formula that I've shown before, that's going to be the voltage, the initial charge plus the new charge, uh, voltage that corresponds to it. And then from the formula again, the voltage drop across the inductor would be this, right? Now, just simplifying it down, what we have is this. And the most important part while doing a transient circuit is simplifying it down to the form where it says this. So it has to be some second differential plus first differential, and then uh, uh, another function times constant, right? So what we have here was this. And then for the second differential, we had 1.25 in the magnitude and the coefficient. So we had to remove this. So we just divide all of the parts of this equation with 1.25, right? Including the other side. It gives out this equation. Now that you have the simplified equation, what does it say? You need, it's going to be in this form, right? And uh, from here, you would be able to find out what sort of system is this. So it turns out whenever z is greater than 1, it's overdamped. Z is equals to 1, critically damped, underdamped for z is equals to less than 1. So it's in this form, and this is the omega squared. So omega squared, we have 8. Omega is going to be the square root of 8, which is 2 root 2. Then this is the 2 zeta. I just write it as C. It's just easier for me to write down. So 2 zeta is equals 2 zeta omega naught is equals to 6. Replacing the omega naught here gives the zeta to be 1.06, which means it's overdamped, right? And then comes in the formulas that you have for the overdamped system. And the solution would be something like this. So this is from the cheat sheet that you're going to be making. It would be super helpful to have something like that. All right. So it was asking for the current. So we replace X with the current, and the times remain the same. And you find out the S1 and S2 using this, which replaces the S1 and S2 here. So it gives out a general equation like this. So now the main challenge is finding K, K1, and K2. So now comes in the part that we talk about the initial conditions and the steady state conditions, right? So what happens after the circuit goes after it's switched, right? After that like the steady state condition for that. So what happens is that uh, whenever you have a steady state DC, remember that whenever there's a DC, the capacitor that was here, it's gonna act as an open circuit. That's why I wrote down as an open circuit. And the inductor that was here, that's gonna act as a short circuit. Just connect the wires. And for the capacitors, just open the circuit. So that's one important thing you have to remember. For DC, capacitor gets opened and the inductors get shorted, just connected, right? So what happens now is that you have a different current path, which is this, right? So Uh, if you see here, what does it say? X at infinity is equals to k. So infinity basically suggests the steady state after the switching, like however long it might take infinity time. So as long as it's open, we're fine, right? So if we are solving for the current at the infinity time, we would find the value for this k. So what happens is that you see that current at infinity, what would that be? It would actually be equals to zero. Why? Because this path is open. This path is open. So where can current flow? It can flow nowhere. It has no path to flow, right? So current has no path to flow. That means current is zero, which suggests that K is going to be zero as well. So you see the significance of having these formulas with you, right? And now you would have to find out the uh, the other two, K1 and K2. So you have K equals to zero, you replace it here. And remember that it was at time is equals to zero. So you replace this equation, the t's with zero. See t is equals to zero, t is equals to zero. What happens is that it gives out another equation that I at the time zero is going to be equals to K1 plus K2. And remember, for these circuits, uh, current doesn't change instantaneously because there was an inductor. So, and uh, considering that fact, and also considering the fact that like we have both current, the capacitor and the inductor, neither the current nor the voltage for this case would change instantaneously. Oh, I think you had a question. How do we determine if it's a sine or cosine for time domain representation? Okay, I'll just finish it off real quick, this one, and then move on to that. Sorry that I kind of missed that out, but I'll address that like right after this one. So here, uh, it's going to be the same at zero minus and zero plus, which means the moment before switching and the moment after switching. So we use the moment after switching to find out the k. So now we can assume that we would be able to find out these two values using the zero minus. So what happens at zero minus, right? At zero minus, this thing was connected, right? So this thing was connected. That means it was flowing. The current was flowing through here. That was a whole circuit, right? And then you have 12 volts, 6 volts. So 12 volts plus 6 volts over this resistance, 6 ohms, gives out 3 amps. So basically that's the current that flows at that zero minus. And we just replace it in the equation, uh, 3 amps. I'm just trying to follow up. Okay, what is being done here? Okay, so this step might seem a bit more complex because what happens is that we're using the formula we did before as well. If you hit like the first step, and then replace the values as usual. Same thing. Don't think that this is different. This is just 12 volts PR, the 6.6 plus the 1.5 is a 7.5. 6 farads is the capacitance that was there. 1.15 Henry was the inductance for the inductor. And then from the formula, this remains. So we need this di by dt, which comes out as negative 3.6, right? And then what happens that just keep this in mind. I know it gets a bit complicated at this point. What happens is that when you have this equation from here, right? To get rid of the exponential here, what you do is you take the differential on both sides. Differential on both sides. And what happens is that this exponent comes in front. This is more like Calc 2 stuff at this point. So it comes in front, and you have the negative 2t is 0, remember. So comes here, now it comes here, and then we have the negative 4 here, and the di at 0 and dt. That which we found here comes here. This gives out 3.6, negative 3.6 equals to negative 2k1, negative 4k1. We have negative in front of all the numbers, so we can just get rid of them by multiplying negative on the both sides. And then you have the one that we did here, equation 1, and then the equation 2. Solve it simultaneously. You get k1 and k2. Then you have the equation for it using the k1, k2, and the k we found before. Uh, Even though I make it sound simple, it's not that simple. I know it takes a while to understand. It gets super complicated. And now, I hope that made sense. If you have any question about this, feel free to ask so. And otherwise, I'll just go into explanation. How do we determine if it's a sin, if it's a sine or a cosine for time domain representation? Do I have that? Okay. So I think this is the question that you guys were asking about. So what I'll do is I'll have it both sideways. One, 1 second. Let me arrange this real quick. So we have the presentation here. Okay. So we have this frequency. Okay. So the question is, why do we uh, cosine instead of, or how do we determine if it's a sine or cosine? So, so when So that's a good question, actually. So this involves a lot of complication. So let me make it clear. Give me 1 second. I do have a quick quick reference to it. I remember I used to struggle with it as well. All right. So from what you see here is that in like you can assume it to be cosine always. Like you can start off as cosine, but you can also represent it as sine as well. So what happens is that it's basically not it's a tough thing to understand and um, tough to connect the dots. Why is it like that? But the easy fix is that whatever you write here, you would just have to add or subtract a 90-degree angle in that. Yes, you are right. You can represent it anyway, just need to make the phase shift, if that makes sense. Yes. But careful about the phase shift. It's really easy to mess it up. So you gotta be super careful about that. So that's the only difference between 180. Not sure what you meant by -80 and 180. Oh yeah, yeah. So that's the thing. So it's always the reference angle. Like it's not uh you would have to take it from other side. For example, like uh suppose you have 225, right? 225 would be somewhere around here. So that the reference angle would be actually 45. And if you remember from trigonometry class, there's something called all sine, tangent, cosine, I believe. Was it? Let me check. I forgot about this. Quadrant rule. Yes, I think it was all sine. Yes, all sine, tangent, and cos. So it's always better to deal with the. I believe they wouldn't ever have angle more than 180-degree because that's not the proper representation. But even if they have it, you can just change it to a sine or cosine using again this formula again. So first change it to like a angle smaller than 180 using this formula. So uh, if it's more than 180, just apply this first, and then if you want to represent in cosine or sine, you can basically use this one right here, if that makes sense. All right. If you guys have any other questions, awesome. So that's clarified. If you have any other questions, you can leave it down in the comment right now, or just come off mute and ask it, whatever's easier for you. Otherwise, I'll be ending the session in 1 minute. I'll just wait 1 minute for you guys to say if you have any questions. So I'll be closing the meeting at 1:26, if that's okay with you guys. Awesome. So it seems like you don't have any questions. If you want the recording of this video, make sure to put down your name in the Excel sheet link that I've given. Or if you had registered already using the QR code that was sent to you, you would also be receiving the recording as well. All right then. Uh, can you go over the Bodhi plot one more time? Oh, okay, sure. So it was actually not high pass, it was a band pass. And why was that, right? I highlighted high pass because I was trying to differentiate how does high pass look like. So this one was actually a band pass. Why is that? It's because this is letting one band of this frequency pass, if that makes sense. And high pass would be uh just something on this side. I hope that answers your questions. Would the high pass ever come down? For sure, yeah. High like it will be the high pass would be down at lower frequencies. So I'll just do one thing. I'll just erase this one and show you how it would look. So it always has a reference frequency, right? So uh how would you know if it's a high pass or a low pass? So it always has a reference frequencies. For example, like if you have a range between like what, like 1 to 1,000, you can assume that the higher frequencies would be the one that's called high pass. So if I had a here something like this, that would be a high pass. And to answer your question, where you asked like if high pass ever comes down, you can see that high pass is down here, like at the lower frequencies. There's no magnitude, right? It's not it's not ever getting reflected in the body plot. So which means that the frequencies, the signals at these frequencies are stopped. Like those are uh like to answer your question, it comes down, right? The magnitude doesn't go up because these are stopped. So that's going to be on high pass. Uh, does that answer your question? So see, it's got a lower starting because it's not hitting the low frequency pass. Lower starting. Starting. Uh, uh, uh. Oh yeah, you're right. Yeah. Then goes up because the high frequency is going through. Yes, you're right. And I believe you're talking about the high pass that I drew, right? Yeah. Okay. If that's the case, yes. Right. Since the band pass was just the one that was initially there, now it's going to be a high pass. And this is basically just 2 points question. So this should be something that you would probably have to answer out of your intuition. Nothing to work out. Just you see which sort of frequency is passing. If it's on the higher side of the frequency range, it's a high pass. If there's a curve on the left side, on the lower frequency side, that would be a low pass. And the previous one, which was the band pass for us. So that's gonna be basically it. Like, shouldn't be too much of a challenging question, at least for this one. But I would really definitely ask you to go through the 40 plots lectures, because there could be questions about uh, quad zeros, quad poles. The questions I had here were fairly simple, and I believe because during my time, Professor uh, did do some quizzes on the body plots and some assignments, so he didn't focus much on giving body plots question in the exam. So I can assure you that's going to be the same case for you. So better be prepared for the worst. Yeah, like if a challenging question comes on, uh, be sure to make sure you know what's actually going on. All right. Any more questions? If you guys are all good, uh, I'll be ending the session in 2 minutes. Okay. So yes, shoot up your question.
Okay, so I guess my question would be, can you hear me?
Yeah, I can.
Okay, sorry. Um, my question is just in regards to more like the structure. So I know that the exam's supposed to be what, an hour 50 or so.
Uh-huh.
Um, did you take the class within the last couple years?
I took it back in 2023, so 2 years ago.
Okay, yeah, for sure. Um, so I'm taking Scrummy, and I know that is there a coordinator for this class? Because usually if there's a coordinator, all the exams are the same.
Nope. There is a coordinator, but it's usually just Marnie Wong. But each professor has a different question. I can say that for sure. And Brian
Okay.
Scroomy has one of the toughest ones, from what I know from my friends.
Okay, yeah, for sure. Is there anything in specific, or maybe like some general concepts that would just be good to review? Because obviously, with the time constraint, they can't ask, incredibly long questions,
For sure.
because there's going to be, a few of them on there. So, things like Laplace analysis, where it would take a very long time to do a lot of conversions, or like a KCL where you have to fully solve it out. Would we see something like that, or would we see more like setups for free response?
So, I can't say for sure about Brian Scrummy because I've never seen his exam papers. The only class I took this James McDonald class back in 2023, and then I TA'd for another professor called Ahmed Iwaisha. But I'm not sure about Brian Scrummy. But from what I feel, like, don't quote me on that. Like, I'm just saying, like, I feel about it, but not sure what's gonna be in the exam. But I feel like there. I think it's a good idea to go over the body plots, and I usually see the trend that professors try to include stuff from the, like, I believe you had a midterm, right?
Yeah, that's correct.
So they usually try to like put up more stuff that's not been in the midterm. So whatever was not
Oh,
covered in
okay.
the midterm, they would probably focus on that more. And for Laplace, from what I can say about my experience with the two professors, they didn't have anything like out of your mind, or like anything like that's gonna take up a lot of time. It's more just, like how you have
More
the S representation and then you have to change it to the time domain representation. That's it.
okay, so just more basic concepts there, not like fully solving out, more like just transformation, or if we were doing like, I don't know, like a first order plot where we have to find, the time at zero minus and then at infinity or something like that.
Yeah, from my experience. Yeah, I'm not super
Okay.
sure about Scrummy, but I'm not sure if he has practice exam questions.
Yeah, we were given a review guide, and we spent a couple hours on that yesterday. But I'm more concerned if it's going to be like because I think it's supposed to be cumulative, correct? Or is that more
Yeah, it
a
is. I
professor
think
thing?
all of the circuit exams are cumulative, but
Cumulative,
yeah, I
okay.
mean, I think the concepts build up, right? Like, if like Devin and Norton, they probably didn't cover it like in the recent times, but that's something they would expect you to know. Maybe
I see.
they can, from what I remember, there could be some question that combines Devin and Norton with AC circuits. So basically testing your knowledge, your concepts within Thevenin and Norton and also AC at the same time.
Awesome. All right. Yeah, for sure. Thank you very much. Really
Yeah,
appreciate
for
the
sure.
help.
Yeah, for sure. Yeah, happy to help. All right, guys. If you have any other questions, like next semester or anything, if you need help with any triple E course, or if you're in mechanical, feel free to stop by at our tutoring center. It's at ECG 104 and 152 in the Tempe campus. Or you can also find us online. If you search up FSC Tutoring Center, you should have the link to join the online tutoring as well. So we have tutors most of the time in this, like in the week, including weekends. So, yep, if you have any questions there, and we're closed already because we're not open in the finals week because all of our tutors are students as well. But next semester, if you need anything, feel free to stop by. And if you have any suggestions, also please let us know. Yep. All right, then. Good luck on your finals. I would suggest trying to relax a bit before the circuits exam. It's usually uh, an exam that takes a lot of thinking and having a clear mind. So practice a lot before the exams, but try to rest also before the exams. That usually helps me a lot. And yeah, good luck. And if you have anything, feel free to email me. I can't guarantee that I can reach out back to you for next 2 days because I have exam as well. But I'll try to help out my best. All right then. Till then, take care. Bye bye.
Awesome. Thank you so much. Bye bye.
Yeah. Bye bye.